Question 22, part A, wants us to write an equation for incomplete combustion of heptane. Incomplete combustion, remember, means that when the substance burns you produce carbon monoxide or carbon rather than carbon dioxide. So you can choose either of those, so let's go for carbon monoxide, but it wouldn't have mattered. So heptane is C7H16. You don't have to draw the structure for this one. Most equations, it's crucial in organic chemistry that you do show the structure, but because you're destroying it all in a burning equation, you just put the molecular formula in, because that's going to help you get the balancing right anyway. And remember that you can apply the CnH2n plus 2 general formula to work that out, because heptane tells you it's 7 carbons, so double that and add 2 and you get 16. So that's the molecular formula for heptane. So that's going to be reacting with some oxygens to give you CO, because it's in complete combustion, and water. So these numbers are easy to get because you've got 7 carbons, so that means we've got to have 7 carbon monoxides to balance that. We've got 16 hydrogens, and that's 8 lots of 2, so we've got to have 8 H2Os. So we can then just add up the oxygens. 7 there plus 8 makes 15. And 15 is 2 lots of 7.5. So 7.5 O2s equates to 15 oxygens, and that balances it. Okay, the second thing in part B is that it asks us to explain these different boiling points. So this is really a gift of a question, because this is very easy first year stuff, provided you've practiced the sort of way to set these things out. So if we start with the 2 hydrocarbons, hexane and heptane. So for hexane and heptane, identify what kind of forces have to be broken in order to boil them, and those are induced dipole-dipole forces. Don't write down some horrible abbreviation for that. If you don't write it out properly, they won't give you the mark. So induced dipole-dipole forces have to break to boil. And the point is that heptane has the extra carbon. The important thing about that is that it means that the heptane molecule has a bigger surface area for contact with other molecules, and that's what you need to spell out. Just saying it's a bigger molecule or a longer molecule is not enough. It's the surface area for contact with other molecules. That's the key phrase. So you say heptane has an extra carbon, which means that it has a bigger surface area for contact with other molecules. And because induced dipole-dipole forces operate from every point on the surface, the bigger the surface area, the more of them you have to break. Okay, so more induced dipole-dipole forces have to be broken. And remember that the link between these intermolecular forces and the boiling point is the amount of energy you need to put in to break them. And that's what you need to talk about explicitly, so you have to talk about energy. So more induced dipole-dipole forces have to be broken, and hence more energy is needed. And that's why heptane has a higher boiling point. Okay, so that's the standard kind of discussion for hydrocarbons. Has a higher boiling point. And then pentan 1-ol is obviously different because it's an alcohol. It's got the OH group. So we say that pentan 1-ol has an OH. And of course the key thing for that, which affects the boiling point, is that means that it can form hydrogen bonds, as well as induced dipole-dipole forces. Not instead of, obviously the rest of the molecule, the carbon chain can still form those as well, but it can form hydrogen bonds as well as induced dipole-dipole forces. Okay, so we got that. And the point about hydrogen bonds is that these are stronger than induced dipole-dipole forces. So hydrogen bonds are stronger. Much stronger. And so take much more energy to break. And that's why pentan-1-ol has, as you can see, by far the highest melting point of the three. So take much more energy to break. And that's why pentan-1-ol has the highest boiling point. So you can see you have to be quite thorough, but it doesn't mean you have to write absolutely tons. Okay, so it's not a sort of one-line job. You have to really spell things out fairly thoroughly. Make sure you've mentioned the kinds of forces being broken. So you've got to have that induced dipole-dipole forces in there. You've got to have hydrogen bonds in there. You've got to have the comment about the bigger surface area for contact, explaining why heptane has a higher boiling point than hexane. You've got to relate that to the amount of energy needed to break them, and you've got to get the idea that the hydrogen bonds are much stronger, so again that takes more energy. So there's a lot of points to get in there, but you can say it all in a reasonable amount of space. If you practice questions like that, they're a gift because you can rattle through all that really very quickly. Part C, we have to use these elemental analysis data to figure out a possible structure for this compound N. So the first thing to do is to, as always, when you see masses, turn them into moles. But having got the moles of carbon dioxide and hydrogen, what we're actually interested in are the moles of carbon that this came from. And, let's start this again. Right, part C, we have to work out a possible structure for this compound N. So the place to start is to use these amounts of carbon dioxide and water to figure out the number of moles of carbon and of hydrogen that there are in there. So we know that each mole of carbon gives you a mole of CO2, so we can write that the moles of carbon is equal to the moles of CO2, which is mass over mR, usual thing, equal to 2.97 over 44.0, which comes to 0.0675. Okay, so that's our moles of carbon. For moles of hydrogen, it's just slightly trickier because each water contains 2 hydrogens, so there'll be twice as many moles of hydrogen as there are actually of water. So we can write that down as well, that the moles of hydrogen is 2 times the moles of water, which is 2 times, again, mass over mR, so 2 times 1.62 over 18.0, and that comes to 0.180 moles of hydrogen. Okay, so we've got the moles of carbon and hydrogen. Now the complication is that the compound also contains oxygen, but we can work out how much of that there is because we can work out the mass of the carbon and hydrogen from these numbers, and the difference from the total mass, which is 1.71, is the mass of the oxygen. So let's do that. So we can get the mass of carbon plus hydrogen. It's going to be, well, 0.0675 moles of carbon. So if we multiply that by 12, which is the atomic mass of carbon, we'll get the mass of carbon. So it's 0.0675 times 12, plus that many moles of hydrogen. Each mole weighs 1 gram, so that's 0.180 times 1. And if we just add that lot up, that comes to 0.990 grams. Okay, so the difference between that number and the total mass is the mass of oxygen. So we can say that the mass of oxygen is equal to 1.71 minus 0.990, which is 0.72 grams. And we can turn that back into moles, and then we'll have the moles of each of the elements, which is what we need. So we get moles of oxygen is mass over AR. Okay, is 0.72 over 16.0, which is 0.0450 moles. Okay, so now we have the 3 moles, and we just need to work out what these are relative to one another in whole numbers. In other words, work out what the empirical formula is. So we could neatly do that in a table, which is what we're used to doing with empirical formulae. So if we just put carbon, hydrogen and oxygen across here, we can write down the moles that we've now calculated. So we have 0.0675 and 0.180 and 0.0450. And we just do what we always do in these empirical formula things, that we just divide through by the smallest. And if you do that, you get 1.5 and 4 and 1. And obviously, because we don't want the 0.5 there, we can easily get rid of that by just doubling each of these, so that keeps them in the same ratio, but then gives us whole numbers. So we just go times 2, gives us 3, 8 and 2. So that means that the empirical formula is C3H8O2. But that's also the molecular formula, because if you add that lot up, that adds up to 76. So this gives MR of 76.0, which agrees with the number it told us, which therefore means that this is also the molecular formula. Okay, so we needed to establish that, not just assume that. Okay, because you have to show explicitly that you've taken the MR into account in deducing the molecular formula. So all we need then is a possible structure for a compound of C3H8O2. And there are various possibilities, but if we have our chain of 3, it's a saturated chain, you can tell by counting the numbers of hydrogens. So we could, for example, have that compound would be a candidate, and if you just double check your numbers of hydrogens, that indeed comes to C3H8O2, so that would give you full marks. Right, part 2 is a tricky little question where we've got to figure out an equation for making that compound, Sol-Ketel, from propan 1,2,3 trial. So obviously the first thing to do is make sure we get the correct structure for propan 1,2,3 trial. So propan means a saturated chain of 3 carbons, and 1,2,3 triol means that it has an OH on each of those carbons, so it's that compound. Now the thing to do is to recognise that this also has 3 oxygens on adjacent carbons, so that carbon has an OH, that carbon has an oxygen, and that carbon has an oxygen. So I think the thing to do is to redraw that in the same kind of arrangement as this, because that makes it sort of easier to see what's going on. So we think, right, we've got, there's carbon 1 with its OH, this will be carbon 2 with its OH, and this will be carbon 3 with its OH. So that's propan 1,2,3 trial, but now drawn in the same arrangement as that. And once you do that, it's kind of easier to see what's going on. Now it tells us that we have to react it with a carbonyl compound. Now it's important you know that that phrase carbonyl compound specifically means aldehyde or ketone. It doesn't mean anything containing a carbonyl group, so we don't want, carboxylic acids or acyl chlorides or anything like that. It's got to be an aldehyde or a ketone. And if you look, you can see that there are 3 carbons to come in there. So if we put those 3 in there, that's the carbons in place, and it's got to be a carbonyl compound, and you can sort of see from the symmetry that the carbonyl group wants to go in the middle. If we put it at either end, we're not going to get this sort of symmetrical structure. So if we put the carbonyl group here, then you can sort of see from the symmetry how you're going to get from there to there. And then you just really look at what the difference is. So you can see these two hydrogens from the OH group have to be lost, and the oxygen from the carbonyl group has to be lost. So basically, we've got to do a condensation reaction in which that lot gets condensed out to make a water molecule, and you can see then that what will be left will actually condense together to give you that. Okay, so that's what you want then. So your equation will be this, which is propan 1,2,3 trial plus propanone gives you your sol-ketal, and we've condensed out a water molecule in there, and so that's the equation you want. In part D, we have to use these elemental analysis data, mass spectrometry data, and proton NMR to figure out the structure of this compound. When you get a question like this, combining data, the important thing is that to get all the marks you have to interpret all the data. So don't try and cut corners and think, for example, oh, I'll just try and work it out from the NMR, I might not need that. That may be true, potentially, but if you don't do the analysis on that, you're not going to get the marks anyway. So you may as well just get stuck in and do it. So if we do the elemental analysis first, because it's always easier to interpret the NMR when you know what the molecular formula is. So we do this normal empirical formula method. So we have carbon, hydrogen and oxygen, and we just copy down the percentage masses. So 54.54, 9.10 and 36.36. Sorry, there's a misprint there, isn't it? It should be 36. And we just do what we normally do, which is divide first of all by AR, which gives us 4.545 for carbon, and of course 9.10 when you divide that by 1, and that gives us 2.273. And then we divide those through by the smallest of them, which is this one. So that's going to give you 1 and 2 and 4. Okay, and then you have to explain, don't just leave it as a table like that, you explain that that means that the empirical formula is C2H4O. The next job is to turn that into the molecular formula, and that means we need the MR. So you have to explain how you know what the MR is. Don't just say MR is 132, because the risk is they'll say, how do you know that? So you have to explain that because the molecular ion M over Z is 132, that implies that the MR is 132. Okay, so you've got to actually make that statement. So if we add up the MR of C2H4O, that is not going to equal 132, so C2H4O gives an MR of, well, I've got 24 plus 4 makes 28, plus 16 for the oxygen is 44. And you can see that if you multiply that by 3, you get 132. So we could write that 132 over 44 is equal to 3, which means that there are 3 lots of C2H4O in the molecule. And that means that the molecular formula is C6H12O3. Okay, and that's then our starting point for interpreting the NMR data. I always think it's a good idea to label the peaks on the spectrum A, B and C, or whatever, so that it's immediately obvious which peak you're talking about. But if you're going to do that, just tell the person marking it that you've done that. So just say that you've got peaks labelled A to C on the spectrum, and then they know to look for those when you're talking about them. Now, I would be tempted to start with the fact that you've got 2 split peaks, and they must come from CHs that are next door to each other in order to cause that splitting. So you can get a big chunk of structure straight away by just looking at what A and C give you. So if we start with A, it's got an area of 1, which means that there's 1 hydrogen contributing to it. It has a quartet splitting. So use the technical term, don't say split into 4, they like you to use the proper terms. So it's a quartet, and that means that there are 3 hydrogens on the adjacent carbon. And it has a chemical shift of just over 4 ppm, which when you look at your data sheet tells you it's got to have an HCO shift. Which is 3.0 to 4.3 ppm. So that information actually gives you a huge chunk of structure straight away, because we know that we've got a CH, we know that it's got a CH3 next door to it because of the quartet splitting, and we know that it has an oxygen attached to it. Okay, so we can get all of that, and of course we know because carbon forms 4 bonds that there'll be another bond there to something else, and there'll be another bond here to something else. So we can get that just by looking at pK. Okay, so that's the structure that we can get, and this hydrogen is the one that gives you pK. So now it's obvious that this CH3 comes from peak C, but we should spell that out, okay, make it clear that we've recognised that. So that must come from peak C, and we can just document the detail for that. So peak C has an area of 3 because of the 3 hydrogens in the methyl group. So we can say that. We can say that it's a doublet due to the 1 hydrogen on the adjacent carbon. Okay, which is, sorry, that 1 hydrogen there is causing those 3 to split into a doublet. And we can say that it has an HCR shift, which is 0.5 to 2 ppm, and you can see that peak C falls comfortably in that range. So that hasn't actually taught us anything we didn't already know, but it needs to be there just sort of for completeness. So that leaves now peak B, and we've got to think, what can we say about that? Because that's obviously going to be from a different bit of structure. So B has an area of 6. Now when you see an area of 6, 6 equivalent hydrogens is most likely to be 2 equivalent methyl groups. Because it could be 3 CH2s, but that requires a very high degree of symmetry. You can see from this that this molecule doesn't look like it could be symmetrical, because you can see that you haven't got any sort of symmetry there at the moment. You've got 3 different groups around there. So almost certainly B is going to be 2 different methyl groups. So you could say due to 6 equivalent hydrogens, and that's likely 2 methyl groups, and that's what you should always be looking for if you've got an area of 6, or 9 would be 3 methyl groups. It's a singlet, which means that there are no adjacent CHs. And again, it has an HCR shift. Which is 0.5 to 2 ppm. So what does that tell us? Well, it's not quite as definite as this one, but we have a pretty likely candidate for what that tells us. Because if the 2 methyl groups are equivalent, then that either means that you've got a very symmetrical molecule where they're in sort of symmetry related positions, but as we've said, this doesn't look symmetrical because you've got no sign of symmetry there. So the other way you can get it is if they're both attached to the same carbon, and that seems much more likely possibility. So that suggests that we have this arrangement where you have two methyl groups bonded to the same carbon and therefore equivalent to one another. Okay, so that suggests that we have that arrangement, and whatever is attached at these two positions, there are no CHs there. So we've got two fragments of structure that we can now put together. And we've got one more bit of information from the NMR, which is that we've got two peaks which disappear when D2O is added. Now remember, that's what OH and NH peaks do. We've got no nitrogen in this molecule, so that suggests that we've got two peaks that disappear in D2O. Means that we have two OH peaks. Now if we look at the chemical shifts of those peaks, they're quite significant, because one is at 11 ppm. Now if you look at your data sheet, that could in principle be any kind of OH, because the OH range goes all the way across the top, but if you look at that very extreme end, you can see that it's very likely to be a COOH. That's very characteristic. It would be a big surprise if it was any other kind of OH down there. So 11.0 ppm suggests that there's likely a COOH, and the other one is at 3.6 ppm, and that's not in the range for a COOH, so that's likely to be an alcohol OH. Okay, so we've got those four bits of structure together to put together now. We've got this, and we've got these two OH groups. Now we know we've got an oxygen there, and we know we've only got three oxygens altogether. So if we have a COOH, this will have to be the third one, and that means that that will have to be an OH. So we can now add that onto the structure and suggest that that is likely to come from the peak at 3.6 ppm, which disappears in D2O. So now we've just got to attach this element of structure and the COOH to that, and you can see how they're going to fit together. So if we just rub this lot out up here to make a bit of space, you can see this carbon has two things attached to it. So if we draw that in the middle, then we can attach this lot on one side. So we get COH, CH3H. Okay, and on the other side we have the COOH. And that appears to fit everything in the NMR. We have to check that it fits the molecular formula. So we count the carbons, 1, 2, 3, 4, 5, 6. So that's good. It's got the 3 oxygens. And if we count the hydrogens, we find there's 12 of those as well. So that's your answer. That should be enough to get you full marks. But if you have time, it would be sensible to just produce a sort of version of that which makes it absolutely clear which hydrogen corresponds to which peak. So make sure that structure is clearly identified as your answer, but then it's worth, if you have time, don't worry too much about doing this, but just to make it absolutely clear for the person marking it, I think it's worth going through and just making the connection and saying, right, that hydrogen is peak A, those 3 are peak C, this one is the 3.6 ppm peak, this one and this one collectively give you peak B, and this one gives you your 11 ppm peak. And that's your answer. So the thing about NMR problems like this is you've got to try to build a structure up. You're not going to get many marks just for listing things like, you know, this peak is a quartet because there's 3 hydrogens on an adjacent carbon. In the old days, if you're looking back at older questions, they used to give you marks for that, but they expect more now. They expect you to be making the connection to bits of structure. So do the sort of thing like we did there, to use the splittings and the chemical shifts to build up as much structural information as you can as you go through one peak at a time. And usually you won't be able to build up the whole structure in one go. You have to build a little bit like this, then build a separate little bit like this, get the COOH separately, and then you just look at how they fit together. So drawing on these empty bonds is quite important, so that you remind yourself, oh yeah, I've got to find 2 things to attach there, I've got to find 1 thing to attach here. Okay, and if you do all of that, it's actually not that hard to put that structure together.